So let me share the screen here. Plus. So hi everyone. So welcome to the ninth live session of this real analysis course. Okay. So um, so today we are going to look back some another properties of differentiation that we had not done in the last live session. Okay. So um, okay. So let's start with some basic problems and gradually we will increase the difficulty level. Okay. So yeah, once again, let me check on. Yeah, it's proper recording. Yeah. So okay. So let's start with some applications of Lagrange's mean value theorem. Okay. So can anybody please confirm that whether am I audible or not? Probably. Yeah, Monica is there. So Monica, can you please confirm whether this screen is visible and
Yes, yes, you are audible.
okay. So first we are going to see some applications of Lagrange's mean value theorem.
Okay.
I hope you know the statement of Lagrange's mean value theorem, right?
Yes, yes.
So first, using this Lagrange's mean value theorem, let us see how we can show that 2x by pi is less than sine x for 0 less than x less than pi by 2. Okay. So since it is the first problem in our discussion, I mean, since this type of problem is the first problem, so this problem I will solve, and the next problem you should try to solve by yourself. If not, then I will solve. So, so for this type of problem, first we start with the function so that we can use the Lagrange's mean value theorem. So let's take fx is equal to sine x minus 2x by pi. 0 less than x less than pi by 2. So obviously f is continuous on third bracket delta pi by 2 for some delta get approached. So put f dash x to be, so obviously x dash will be what? X cos x minus sine x. Sorry, it's my mistake. We should take fx to be sine x by x, not 2x by x. Sorry, it's my mistake. So the f dash x to be x cos x minus sine x by x squared on third bracket delta pi by 2. Now, so just observe one thing that I mean, it is quite known that x less than equal to tan x for 0 less than x less than pi by 2, right? Correct? Do you know this?
No. Yes, yes, yes.
Yeah. Okay. So this is x less than 10x less than pi by 2. So now look at this f dash x. Now since x less than 10x, this implies what? This implies x cos x less than sin x, right? So this implies what? This implies f dash x is less than 0 in delta less than x less than pi by 2. So f is strictly increasing function on open 0 third bracket pi by 2. Okay. Increasing is by mistake again. It's decreasing because it is less than 0, right? As f pi by 2 is equal to 2 by pi, so fx is greater than 2 by pi on 0 less than x less than pi by 2. So this implies 2x by pi less than sin x for 0 less than x less than pi by 2. So, let me repeat the whole solution here. First, we have started with a yeah. First, we have started with an fx is equal to sin x by x. So, on which we are going to use the Lagrange's mean value theorem. Okay. Now, so obviously, if it's continuous, now look at f dash x. Now, since x less than 10x for 0 less than x less than pi by 2, so this tells that f dash x is less than 0. This implies f is strictly decreasing function. So, and as f pi by 2 is equal to 2 by pi, so fx greater than 2 by pi on 0 less than x pi by 2. So, this implies 2x by pi less than sin x. So, do you understand the whole solution? Yeah, I'm waiting for 3 or 4 minutes. Please go through the solution once again. If you have any doubts, let me know. Okay, you can take your time.
Yeah, that's clear.
Okay, so yeah, let me search the second problem. But for some tips. So, start the next problem, which tells that x by 1 plus x less than log 1 plus x less than x for all x probability. So just can you please think for some minutes how to approach this type of problem? I mean, at least you can try for some minutes. Or I mean, do you have any idea how to approach this type of problem? Any idea?
We can take function as log of 1 plus x upon x.
Yeah, you are almost correct. Yeah, you are almost correct. But the easy way is to do the plus minus. That is log of 1 plus 6 minus 6, right?
Oh,
Yeah. So you're right, correct. So here we are going to do the first f dash x, which is 1 by 1 plus x minus 1, which is nothing but minus x by 1 plus x, which is less than 0 for all is greater than 0. So this implies f is decreasing function. So yeah, and obviously f0 is equal to 0. So for all x greater than 0, fx is less than f0. So this implies log 1 plus x minus x less than 0. And this implies log 1 plus x less than x. Yeah, right. You are correct.
mm.
Yeah. So and what about so this part is done. So what about the other part? And what about the other part? So in the so in other the other part also, sorry, yeah, the other part for the other part also you can choose the gx to be log 1 plus 6 minus x by 1 plus 6 and do the same way, but just you can first I mean just you do this right now, okay?
Mm.
Take your time, you do this and let me know, okay?
It's increasing function.
Yeah, right. So yeah, so let me write down the solution. So
Gx is positive. Gx is greater than g of 0, and g of 0
uh,
is
g dash x is equal to 1 by 1 plus x and
yeah, it's proved. Log of 1 plus x is greater than x upon 1 plus x.
yeah,
Or
right.
I can say x upon 1 plus x.
So sorry, this is x by 1 plus x square. When you're greater than 0, so yeah, so you're done. You're
Hmm.
right. Good. So the next problem, yeah. Okay, so to prove that 1 plus 1 by x into the power x is greater than 1 plus 1 by y into the power y for all x, y belongs to R and x greater than y greater than h. You can take a 10 minutes. Right. So, do you get any way out?
No.
Let's try for some. Okay, so so as usual, here we also start by defining fx is equal to 1 plus 1 by x to the power x. Our claim is to show f is monotone and equivalent. It's a slightly tricky problem actually. So let's see. So first, if dash x is equal to 1 plus 1 by x to the power x, log of 1 plus 1 by x plus x dot 1 by 1 plus 1 by x into 1 plus 1 by x squared. So this is what? This is 1 plus 1 by x to the power x. Log of 1 plus 1 by x minus 1 by x by 1 plus 1 by x. So basically it's basic calculation and finally this gives nothing. I mean this is it. Okay. So now define phi x to be log of 1 plus x minus x by 1 plus x. Remember the thing is here we are, I mean yeah, here we have 1 by x, here also we have 1 by x, and here also we have 1 by x. That's why we are defining this function in this pattern. Okay. So and obviously on the domain uh, x greater than equal to 0. Okay. So now now obviously phi is continuous on third bracket 0 infinity, and phi dash x is equal to 1 by 1 plus x minus 1 plus x whole square, which is equal to x by 1 plus x whole square greater than 0. Sorry, it's not that. It will be equal to x by 1 plus x. Sorry, it's x by 1 whole square. Sorry, greater than 0.
This is exactly the previous one.
Yeah.
Log
It's
of 1
the
plus x
yes,
minus
it's right.
x upon 1
Right,
plus
right.
x. But I didn't get why we have defined this phi x.
Oh, actually, the point is since we have, I mean, so the point is since look at this the inside portion of f dash x.
Okay.
Actually, this part. So we need to check this part is more or increasing or decreasing or what. So, but the point is that since we have done the problem two, I mean previous problem, so from that we can directly tell that okay, this portion is more increasing for them who had not done the first part. So it is not only looking at this thing, right? So that's I mean our
Okay,
only goal
okay.
is to realize that f dash is monotone. I mean f dash is increasing or not. This is our main goal, or decreasing maybe. Okay, this is our target. So the phi that x is greater than 0. So this tells that phi is strictly increasing. Increasing on third bracket 0. Okay, and as phi 0 is equal to 0, so phi dash x greater than 0, and this implies log of 1 plus x greater than x by 1 plus x. 0. So finally, we get that this log of 1 plus x greater than x by 1 plus 4 is greater than 0. Now look at the expression of f dash x. So the inside portion of f dash is greater than, so f dash is more than increasing. Right. This that's what we need. So so this tells f dash x greater than the, so f increasing for less greater than 0. So a is greater than y implies f5. So this is the way out. You understand?
Yes. Yes.
So now consider the next problem. So now it is a different type of problem. So let f third bracket b to r is continuous AB, and f dash 6 is not equal to 0. If a and fb are this, then there exists unique x naught belongs to open AB such that fx not equal to 0. So just for this, you need to use the Bolzano's theorem first. Okay. So using this and you also using the Lagrange minimal theorem, try to solve this problem first. Take your time.
We can explain it geometrically.
Geometrically, yeah. Now, okay. So, mm,
F dash x is not equal to 0. That means function
yeah,
uh,
means suppose if
slope
so the graph of the function can't be parallel to x.
parallel to x.
Sorry,
Yes.
not the sorry. The
X
tangent of the
axis.
function, yeah, cannot be parallel to x.
Slope is not parallel to slope is
Yeah.
not 0. That means tangent at any not is not parallel to x axis. Tangent at any point between A and B is not parallel to x-axis. And
Yes, right.
F0 and FB are of opposite signs. That means they are in first quadrant and fourth quadrant. F0 and FB, like that.
Yes, right. Correct.
Therefore, uh, there must be at least one point in the graph which cuts
Yes.
the x-axis. At least
Yes.
one point.
Yes. Obviously, definitely. But we need to show that there exists unique. This means unique. There is unique point such that it
Yes,
crosses
yes,
this.
yes. If there are 2 points, then there must be at least one maxima or minima, and there does not. We don't have any maxima or minimum
Yes, yes.
point.
Graphically, yes, yes. I understand. Your way out and thinking is good. Graphically, it is almost obvious, but in terms of writing, how
Theoretically,
you
yes, I have to think theoretically.
yes, yes, your way out is correct, but how to write? Because writing this thing in graphically is not a mathematical way out, right? So how to write it, or which theorems you need to use? Think about it. What take your time. When you know how to write, you need to use some kind of theorems or some other thing. So what are those? Just tell me. That's it.
F dash x is not equal to 0 on AB. That means FB minus FA upon B minus A is not equal to 0. That means FB is not. FB and FA are opposite sign. Therefore, we can say that function is strictly increasing or strictly decreasing
Yeah.
for this interval
But which
A and B. And
which theorem? What is the name
which
of the
one?
theorem?
By Rolle's theorem, I think we can say that.
No, no. First of all, you told that between A and B you will get some x for which f of that equal to 0, right? What is the name of the theorem?
Actually, I can visualize this whole picture, but I can't
Yes.
explain
Yes, that's
it.
right, obviously. But what is the name of the theorem? The name of the theorem is Bolzano's theorem.
Bolzano theorem. Okay.
It is known as Bolzano's theorem. I mean, this visualization is obvious, okay, but there is a name of theorem, it's not Bolzano's theorem, and whatever you have said, it's not exactly nothing but the Bolzano's theorem, okay. So that is the name of the theorem. And okay, so by Bolzano's theorem, fx not equal to 0 for some x naught, right? Now we need to show its uniqueness, correct? Okay, so if there exists y naught such that f of y naught equal to 0, then this implies what? Then there exists some z naught between x naught and y naught such that f dash z naught equal to 0, correct? But this is not the case by hypothesis, right?
Yeah.
Understand?
Yes, yes.
Okay. So yeah, there is, so do you know about Cauchy's mean value theorem?
Yes.
So can you tell me the statement?
If function is continuous in closed interval and differentiable in open interval, then there exists at least one point between open interval A and B, such that f dash C, we can see that point C, such that fb minus fa upon b minus a is
Yeah.
equal to f dash c.
Right. No, 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 no. You whatever you have told is known as the Lagrange's mean value theorem, right?
Yes.
But I am asking about Cauchy's mean value theorem.
Cautious. No, I don't know about cautious mean.
Yeah, okay. Cauchy's mean value theorem is actually generalization of Lagrange's mean value theorem. Okay. Statement is that if AB to R and G AB to R, same hypothesis first of all, such that uh, if G are continuous, or bracket AB, if G differentiable on open interval AB, and third G dash non-zero for all x belongs to open AB, then there exists a point psi, sorry, there is a point eta belongs to open AB such that FB minus FA by GB minus GA is equal to F dash beta by G dash beta. So this is nothing. This is the Cauchy's-Miller theorem. So obviously, it is the generalization of Lagrange-Miller theorem, right? Yeah, right. So, so, yeah. So here is one problem. So, one thing you may ask about its proof. Okay. So you can look at the book Bartlett Shortcut. There you can find the proof. In or anyway, this proof can be found over the internet also. So I am not going to do the proof. I am going to solve some problems. Okay.
Okay.
So let if third bracket 01 Windmill theorem that the equation f1 minus actually equal to 6 by 2x has at least one solution in this. So if it's differentiable and using constant numerator, we need to check the f1 minus f0 plus x has a solution. Think about it. Take your time.
We can take gx as x squares.
Yeah, right. Correct.
And f is a function given.
Yes, it's already given. So there is no
Okay,
point
it's
of
already
taking.
given. Then we can apply Cauchy's mean value theorem.
Yes,
It's
right.
a
Correct.
differential.
Right. Correct. Good. So, so the next problem is that once. What we're calling from. Yeah. Let if be so let if be twice differentiable, maybe, and if A is equal to B. Now, if C is greater than for some C belongs to open interval AB, such that if C is equal to 1 by C minus M into C minus B. Got it. Show that. Uh, So that FC is equal to this thing for some in if uh no, sorry, leave it. If FC is equal to 0 for some C belongs to open interval AB, then show there is some eta belongs to open interval AB such that F double dash eta is less than 0. Okay. So F is twice differentiable and at both endpoints F is 0. And if some intermediate point is F is greater than 0, then we can find eta such that its double derivative at that point is less than 0. Here you only need to use the Lagrange's equivalent theorem 2 times. So let's
Yes.
try.
We do this concept in, I think, maxima minima second differentiability test.
No need to do tests. Only by using Lagrange's member theorem because maxima minima is far ahead of this actually.
No. For maxima minima,
I mean, first of all, maxima minima is, I mean, we don't require all actual maxima minima. Only using Lagrange's minimal theorem we can solve this actually. Yeah, so uh, get this or stuff.
I'm trying actually.
Yeah, yeah, right. You can take your time. If not at any cost, please let me know. Okay.
Actually, I couldn't get it.
Okay. Okay, so yeah. So first of all, here only we are going to use the Lagrange integral theorem. Okay. So f is equal to 0 and f is greater than 0. Okay. So my Lagrange's LMBT Lagrange integral theorem, we can get C1 belongs to A and sorry C such that if dash C1 is equal to FC minus FA by C. One second. So dash C1 equal to FC minus FA by C minus A. Okay. So this will be what? This will be FC by C minus A. And this is obviously greater than 0. Correct.
Yes.
So since FB is greater than FB is equal to 0, so there exists such that dash C2 is nothing but equal to if uh, B minus FC by B minus C. So this will be minus FC by B minus C, and so this is less than 0, right?
Yes.
Because FC is greater than 0. And sorry. So, I mean, now Lagrange mean theorem is C1 and C2 such that if tau dash 3 is equal to if C2 minus if C1 by C2 minus C1. So this is what? If C2, if I mean, sorry, if dash C2 is less than 0 and if dash C1 is greater than 0. So anyway, this whole thing is less than 0, correct? Being my point
Yes.
here? Yeah.
Yes. Yes. Yes.
So, so is what? So if double dash C3 is less than, we need to show. We need to show this thing again. So hence we are done. Now, okay, so yeah, so you know about the desktop maxima minima in case of higher order derivatives, right?
Hmm.
Okay. So consider the following problem. So choose the function fx to be x5 minus 5x4 plus 5x cube plus 10. Show if x if has a maximum at sorry minimum 3 and if either so if x is the function you need to check the if has maximum at 0 minimum at 1 and it has no maximum or minimum at 0. So try it.
Second derivative at 0 is 0, second derivative at 1 is negative, and second derivative at 3 is positive.
Second derivative at 1 is what?
At 1 is minus 10.
Okay, and second derivative at 3.
That is 90.
Yeah. So yeah, so maximum at 1 3 is fine. So what about 0? So you have told us second derivative at 0 is 0, right?
Yes.
So I mean we need to show that it is neither maximum nor minimum at 0. So second derivative is 0. So what? I mean from second derivative you can't decide anything because second derivative is itself 0, right?
Yes.
I mean the point is that if the second derivative at some point is 0, then you really can't decide anything from that. Do you know about that? So if the second derivative is 0, then what to do? What to do?
Then we say that it has neither maximum nor minimum at that
No, no,
point.
no, no. If second derivative is 0, it may have maximum or minimum at that point. It may have.
Okay, then we will go to third derivative.
Yeah, right. If the second derivative is 0, go through the third derivative and check the third derivative at 0 point is 0. If it is non-zero, then on depending on the positive or negative value, we can directly say. If it is 0, then go for the fourth derivative. Understand?
Okay. Okay. Okay.
So point is that look at the third derivative. It's 0 is actually
Third
30.
derivative is 30 at
Yeah,
0.
right. So that's why it says it is non-zero. So the theorem goes if tells that if has neither max nor min. Understand? This is theorem. Third derivative non-zero, neither max nor min. Okay?
Okay. Okay. Yes.
Yeah. So one thing is that so you know about L'Hopital's rule, right? I mean it has been done in the class, right?
Yes.
Then please.
Yes.
Okay. So yeah. So the evaluate the following limits.
X approaches to 0 or
0
0,
plus.
0
0
plus.
plus.
Log of sin x upon cot x. That's zero.
Yeah, right. Correct. So I need to upload this video over the YouTube, so that's why I need to solve it.
I have done by L'Hopital rule.
Yeah, yeah. Okay. So how you have done? So
Uh,
you have
uh,
used that some sin x by x thing, right? I mean log 1 plus x
Derivative
by
of
x.
log sin x at numerator and the derivative of cot x in denominator. Then solved it.
So you have using it you have done it using L'Hopital's rule or without using that?
Using L'Hopital rule.
Yeah, yeah, using only. There is no point of without it. Okay, so but I need to solve this because I need to upload this on YouTube. Okay.
Okay.
So derivative y x 6. Uh, what is the derivative of cot x minus cosec cot x, right?
Minus cosecant square x. Can we do it without L'Hopital?
Without one second. Uh, one second. Without, no, without no, without actually not possible.
By expanding log sin x.
Yeah, yeah, in that way, yes, yes. Okay, so yeah, it's a good idea. In that way, it is possible. Also, let me do it. What is the formula? So actually, see, the point is that the definition is valid for log 1 plus x, right? Log x is
1
not
plus
defined,
x.
correct? So that is another problem. I mean, it will be hard actually. That's why it's better to do this in log because okay. So yeah, now come to the following problem. Let f a b to r be continuous or open interval a b differentiable if a is equal to a, b is equal to b. There exists c belongs to open a b. That's equal to 1. And there exists c1, c2,
What is first part? F dash c is equal to
1.
1.
Yeah. Equal to if plus c1 plus c2 is equal to 1. So the hint is the mean value theorem on okay. This-
First part can be easily done by mean value theorem. Fb minus Fa upon B minus A is equal to F dash C. And Fb is B and Fa is A. Therefore, F
Okay.
dash C is 1.
Yeah, right.
Right.
Once.
And for second part, you have given the hint. Therefore,
Yes.
now I can do it easily.
Yeah, but just do it once.
Surprisingly, it is coming out to be 2, not 1.
It's
F dash C1 plus F dash C2.
okay. So you can get C1 belongs to A comma A by 2 such that this will what B minus A by 2 is equal to A plus C1 and C2 belongs to A plus B by 2 comma B. B minus A of A plus B by 2 by uh, B minus A which is equal to if but or question nothing but If plus b by minus a by b minus a by 2, and this is equal to f of this is equal to b minus f plus b by 2 a. So
F of A plus B by 2 will be cancelled out.
yeah, I understand that. I understand that. Yeah.
And B minus A. That will be 2.
But the question is actually wrong. You are right. Should be two. There's a counter example. Sorry. Example is the following. If you can choose the fx equal to x, so a plus c1 plus a plus c2 can't be 1, right? Correct?
Yes.
So that should be 2. Correct. You are right. Sorry. Okay, now comes to the following problem. So you know about Taylor's theorem, right? I mean, can you recall the statement of Taylor's theorem?
No.
So well, so let me recall it first. So the Taylor's theorem tells that let come to no. Let if real value neighborhood in a of a be such that it's not their differential on it. X belongs to if there exists theta with 0 less than theta less than 1 such that fx is equal to fa plus x minus a f plus a plus x minus a whole square by factorial 2 followed by plus x minus a whole to the power n by n minus 1 factorial last term x minus to the power n into 1 minus theta to the power n minus p n minus 1 factorial if nth derivative of a plus theta of x minus a or p is a positive integer p less than equal to n. Okay, this is a statement of Taylor's theorem. And a slightly modified version is the following. Hmm. All right, this is the fun. This is the fun one. Okay, so these are Taylor's theorem. So using this, uh, prove the following. say net affinity to R be 2y is differentiable on third bracket A infinity, and here exists positive real numbers A and B such that mod fx less than equal to A and mod A plus x less than equal to B for all x belongs to A. Mod if dash x less than equal to 2 root over A third bracket A. So sorry for my bad handwriting, but I hope you can understand. The question is that if is a map from third bracket A, I mean closed A comma infinity to R was differentiable on that domain. So that we and suppose there exists positive integer, there are real numbers AB such that if x less than equal to A and if double dash x less than equal to A. We need to show that if single if dash x is less than equal to 2 root over A. Okay. Only use the Taylor's theorem.
I can't think of it.
Okay. So here is like trick. It's tricky actually. So observe that by what I have written the Taylor's theorem, it will be f of x plus by I mean by that f of x plus h can be written as fx plus h f dash x plus h squared by 2 f dash c for some c inside x and x plus h, right? So this implies what? This implies mod h f dash x equal to mod f of x plus h minus fx minus n by 2 f double dash c. This is less than equal to mod plus h plus mod fx by 2 f double dash c, right? So this implies what? This implies property mod f plus x less than equal to b by h for all is greater than equal to for all is greater than 0. Now since this holds for all is greater than 0, so in particular would h equal to over a by v. So this tells mod f dash x less than equal to 2 root over a v. Okay, take your time.
Yes, that's clear.
Yeah, right. Thank you. So yeah, so there is another problem. If it were be such that if double dash exists in third bracket AB and if dash A is equal to if dash B, show that f of a plus b by 2 is equal to half f of a plus f of b plus 1 by a into b minus a whole square f double dash c for some c belongs to open interval AB. Okay. So only using Lagrange's mean value theorem you can do it. You can put this. So the hint is that by LMDT on the just wait. You can take it back. Create some way out.
Trying. I can take C1 in first interval A2 A plus B by 2 and C2 in A plus B by 2 to B, and then apply Lagrange's mean value theorem. Then I take the function f dash x and interval C1 to C2, and then applied the mean value theorem. But I can't find C2 minus C1. You are not audible.
So sorry for the okay. So sorry, there was a coalition driver issue was that. So the problem is that yeah. So f of a plus b by 2 is equal to f b minus second f b minus b by 2 f dash b, okay, and plus b minus a whole square by 8 f double dash I2 for some I2 belongs to a plus b by 2 power b, okay. So this two equation tells these two equation tells mm, f of a plus b by 2 is equal to half of f a plus f plus 1 by 8 b minus a whole square plus f double dash I1 f double dash I2 by 2, okay. Now obviously if okay, if double dash I1 not f double dash I2, then by intermediate value property the right function with f dash c will be f double dash I1 plus f double dash I2 by 2 for some c I1 side. Therefore, f of a plus b by 2 is equal to half third bracket f a plus f b plus 1 by 8 b minus f whole square. You can see from some c belongs to open interval. If if double dash I1 is equal to f double dash I2, then c is equal to I. And so we are done. Now consider the following problem. So let a belongs to R. Is a real function if p is such that if double dot x exists in a minus h a plus h, some h brother, f of a plus h minus f plus f of h, but h squared is equal to f plus c or some c belongs to minus h. Okay, the viewers, please try to solve this problem. I shall be back within 3 minutes. Okay. that's how to solve this problem. Layout will be is as follows. So what is it? We apply mean value theorem to f a comma f plus h and on a minus h. Now since f of f plus h is equal to f n plus h f plus n plus h squared by 2 f double dash n. Sum a1 belongs to a comma a plus h. And now f of a minus h is equal to f minus h plus a square 2 factorial f double dash a two. Sum a2 by a minus h by so adding this we get f of a plus h minus plus f of a minus h minus 2f is equal to h square a double dash I1 plus f double dash I2. So this implies f of a plus h minus 2a plus f of a minus h factorial h is equal to f double dash I1 plus f double dash I2. This is nothing but f double dash 3 by using min value. So you can put this. So now once again. Mm, okay, let's do a problem on L'Hopital's. Find limit x goes to 0, e to the power x minus e to the power minus x log 1 x by sin x. Now it is 0 by 0 form. So this is limit x equals 0 e to the power x plus e to the power minus x minus 2 by 1 plus x cos x minus, sorry, plus I. Now put x equal to 0. This is what? 1 plus 1 by 2 by 1 plus 0, 0. Sorry, awesome. Oh, no, no, no. So it is also a 0 by 0, right? So again, use the L'Hopital's rule. Limit x goes to e to the power x minus e to the minus x by 2 by 1 plus x whole square by minus x sine x plus cos x. 2 cos. This is equal to 1. Right? Yeah. So yes, one. So that's why I mean for this calculation, but it easy actually. That's why. So now on to the following problem. Evaluate limit x goes to 0 plus x minus. Put f(x) equal to 0, x belongs to infinity, x equal to log x is open. Then limit x goes to plus. Now, 0 plus fx is equal to 0 and limit x goes to 0 minus gx equal to. Actually, this is the answer. So now limit x goes to, sorry, 0 plus x log x equal to limit x goes to the plus log x to 1. So this is infinity form. So this is will be what? Limit x goes to 0 plus 1 by x by minus 1 by x square. Equal to 0. So in this way we can do this type problem. And okay, let's do a easy one. So calculate the limit. Limit x goes to 0, x minus log 1 plus x by minus of x. So now observe that. So observe that is 0 by 0 form, right? Basically, this is limit x goes to 0, 1 minus 1 plus x by 0 plus sine x. So basically, this is what limit x goes to 0, x by 1 plus x times. Now here we can use the following. The limit x goes to 0, 1 by 1 plus x, 1 by sine x by x. So this is 1 by 1 plus 0 into 1. So this is 1. I mean, we have here used the fact that limit x goes to 0, sine x by x equal to 1. The fact. Anyway, we can do it this fact by using the law of equals rule. Okay. Okay, so press plus end here, and this video will be uploaded over the YouTube. Okay. So if anybody in confusion is doubt, please let me know in the next live session. Okay. Thank you.